Today, we are laying out the blueprint for the most ambitious masterclass I have ever created. This is not a tutorial on how to use a web framework. This is a rigorous, deeply technical journey into the architecture of modern software. The syllabus is modeled after the definitive textbook, Designing Data-Intensive Applications. We are going to strip away the abstractions and look at the bare metal. We will analyze the binary formats, the network physics, and the mathematical trade-offs required to maintain integrity when you have millions of users. The course is structured into 3 main partitions. We start with the foundations of single-node systems, move into the chaos of distributed data, and conclude with the complex art of derived data processing. Part 1 covers the foundations. Before we can build a planetary scale system, we must understand how a single machine holds data. Chapter 1 defines reliability, scalability, and maintainability. It sounds academic, but it is not. We will discuss how to define system faults, how to build software that survives human error, and crucially, why you should never trust an average latency metric. We will calculate the P99 percentiles that determine actual user experience. Chapter 2 is data models. We move past the relational versus document debate and look at the underlying structures. We will analyze why document models gained dominance, and where graph-based databases like Cypher actually outperform them. Chapter 3 is the core: storage and retrieval. This is where we learn how databases actually work. We will disassemble hash indexes and B-trees to see how they manipulate hard drive memory. We will contrast the high-throughput write performance of log-structured trees with the read optimization of B-trees. Chapter 4 covers encoding and evolution. We will look at how systems handle binary serialization, the efficiency of protocol buffers, and how to manage schema updates without causing massive production outages. Part 2 moves us into the distributed arena. This is where architecture gets difficult. In Chapter 5, we study replication. We look at the trade-offs between leader-based and leaderless architectures. We will learn how to resolve multi-leader conflicts and discuss the nuances of quorum logic in high-availability systems. Chapter 6 is partitioning, or sharding. We will examine how to avoid hotspots when your data is not distributed uniformly. We will learn to implement hash-based partitioning to prevent bottlenecks. Chapter 7 is about transactions. We will dissect the ACID acronym, but not in a textbook way. We will look at race conditions, specifically write skew and phantom reads, and discuss the isolation levels needed to solve them. The next phase of distributed data is where most developers fail. Chapter 8 addresses the trouble with distributed systems. I will explain why your network is not reliable, why your system clocks will always drift, and how the Byzantine generals problem makes it incredibly hard to define a single source of truth. Chapter 9 is the solution: consistency and consensus. We will study the linearizability model, compare two-phase commit with sagas, and analyze how coordination services like Zookeeper achieve fault-tolerant agreement using Raft. Finally, we reach Part 3. Chapter 10 explores batch processing. We learn how MapReduce, despite its age, still provides the conceptual model for how we process massive datasets across distributed nodes. Chapter 11. Stream processing modernizes the approach. We move from batch jobs to continuous, unbounded event pipelines, utilizing partitioned logs and event sourcing to create a truly reactive architecture. This is a significant undertaking, but by the time we finish this masterclass, your ability to reason about software systems will be fundamentally upgraded. Welcome to the journey. Please like, subscribe, and tell me in the comments which chapter you are most excited for. I will see you in Chapter 1.